Okay, welcome back to the final weeks. Let me share with you a couple of things of what our schedule looks like. I've already sent an email and I made some events on your calendar, so you can see them there, but I just want to go over it. Obviously, today is the 19th. We are going to go over chapter 15 today, which is very short chapter. Once we're done with that, I'm opening it up for any questions you may have. If you don't have any questions, then that's fine too. We can continue next Friday. So next Friday is the 26th, and that's Thanksgiving. So we're not going to be here. Okay. And then the following Friday is the 3rd of December. And at that day, we will finish up chapter 16, which is the final chapter and also a very short chapter. I will also open up whatever time is left to questions and so forth that you may have. And then the 10th is what is called a study day. I will be here if needed. And so that's a good opportunity to come in with any questions you may have, a good opportunity to ask questions for any of the chapters in preparation for the final, which is the 19th. And we don't have Zoom on that day. That's finals week, so that's the final exam. That day, the 19th, everything is due because I need to get the grades tallied up and turned in ASAP. Okay. And so on that day, if you have any assignments that are not done, that's your last day to get them done. In fact, recall that all assignments are still open until the 19th, excluding the exams. Obviously, the exams are a specific day and that's it. So if you have missed some homework in the past, you can still make it up, even though we have 0 on it. Make it up, and then it will be counted as late, but let me know if it's counted as late, and I'll take off the late penalty fee for it, okay? And so that's the last day everything gets turned in. If you're not done the nomenclature, remember the nomenclature exam is you have to get an 80% as per departmental policy. Anything less than that is set back to a 0, so it can continue. You have unlimited attempts. You can continue to attempt to get the nomenclature done all the way up to the 19th, okay? So any questions about that? Any questions? Give you an idea of where we're at. See, I got a chat. Oh, the question is how many questions on the exam? There will be 60 questions, all of them on the final, okay? All of them, it's comprehensive, so it covers all the chapters. Chapter 16 will not be on the final, simply because it's the last chapter and, you really don't have much time to, I think, to prepare for it. But there is homework for chapter 16, okay? So you're only going to be really dealing with chapters 1 through 15. There'll be 60 questions. All of them will be multiple choice, okay? Nothing that you have to write in and has to be graded. So you'll get your final exam result almost immediately. Second of all, if also, do we have to join a Zoom call or to take it on our own time? No Zoom call. It's just like the other exams. It's going to open up on the 19th and it will close on the 19th. That's an important point. Unlike the other exams that are on the weekend, this one opens up in the morning, I believe 7 a.m. and it will close at 11 p.m. on Friday the 19th. So no, you don't have to do a Zoom. Some Some instructors do that. Every time you have an exam, you do in the Zoom, and I'm like, no, it's not necessary. Yeah. Okay. Let's see what else. Good question. 60. Now, if you go to the website, and the link, which again is GCC, but we're using the same material, and it's already there. So we're gonna have to reinvent the wheel to create a whole new website. So if you go to the course website, the link is given on the syllabus. Okay. You will have there a study guide for the final. Okay, to help you out going over questions, going over the material that we're going to cover. Now, keep this in mind. There's 15 chapters, 60 questions. At the most, you're going to see maybe 3 to 4 questions per chapter. Not a lot. Okay. I'll give you an idea. I know some people want to know how many questions per chapter. So there you go. On average, 3 to 4 questions per chapter. But there is a study guide to help you out. Plus, on that website, there are old exams from previous years, old final exams, and regular exams that you can use as a resource. The key has also been uploaded, so you can take a look at those. Obviously, those questions that ask for you to write something in, those type of questions will be readjusted and converted to a multiple choice. But the questions will be very similar. Obviously, the exact question won't be asked, it might be, it'll be, changed a little bit, but you'll get the gist of the type of questions being asked. All right, so this is in preparation. So basically, we're looking at 1, 2, 3, 4, 5 weeks left. Okay, and I'm counting the Thanksgiving week, but if you don't want to count that, then we got 4 weeks left. And again, the 19th today, chapter 15. Any questions you have, I'm open to that after I'm done. The 3rd will be chapter 16. Again, relatively short chapter. And that day will also be opened up after we're done with that, with any questions for anything you have. And then the 10th, I will be here. I'm going to open up the Zoom at 1 o'clock. I'll hang around for about half an hour and see if somebody shows up. In fact, I let Zoom itself be my time clock. I leave it open. The Zoom itself, when there's no activity, will shut off at 40 minutes. So no one shows up at 40 minutes, okay. If that, if you can't make it for whatever reason, but you want me to stay on or open it up later on, shoot me an email. I'm more than happy because, technically I'm here till 3:40. Okay. All right. Any questions about that? Oh, yeah. Now, if you want additional study sessions and questions, you are more than welcome. And I tell this to my GCC students, they can come on Friday, but you're also welcome to come to my Tuesday and my Thursday sessions. I got 2 of them going on. Tuesday, I got one at 1 p.m., starts at 1 p.m., and the other one starts at 4:15. Now, they are complete with, they're done with chapter 15. Therefore, all the rest of those days till the end of the semester, which is the same week of the 19th, theirs ends at Tuesday before yours. So that's their final. But you are more than welcome to, they end on the 16th. You are more than welcome to come to the Tuesday and Thursday sessions, either at 1 or 4:15, because they have study days too. Okay, so feel free to jump in. And no, the question is, do we have class on the 17th? No, we don't. The 17th is just your final, so that's finals week. Okay. The 17th, I think that's the end of the semester, but we meet on Friday, and for some reason, I don't know why, it's happened every semester I've been teaching at SEC. They forget about your Friday class. And, they always say that the end of the semester is either Wednesday or Thursday. And I'm like, no, guys, we're still here because you signed up for Friday, and I won't have you switch your day because you initially signed up, you knew the class starts on Friday and in your schedule, that's what you pick. So we are here Friday, but there's no class on the last day, which for our last day is the 19th of December. Okay. But that is the last day for, that's the final, and we don't have a Zoom. Like most people require a Zoom, you just treat it like your regular exam. It just happens to be a final exam. I believe you have an hour, 50 minutes to complete it. There'll be 60 questions, okay? So give yourself plenty of time to complete that exam, okay? Now, if for some reason you cannot do it on the 19th, keep in mind, I cannot move it after the 19th, but I can move it before. So if you want to take the final before the 19th, shoot me an email through Canvas, let me know, and I'll open it up for the day that you select. But I cannot open it after the 19th because technically, as they tell me, school's over the previous either 17th or the 18th in the semester, okay? Plus they want my grades in, I believe, the next day, so. All right, so does that answer that question? Emma? Yeah. Okay, good. All right. Any questions about what we got left? You know, everybody knows. I have these days put on the on your calendar on the Canvas course, so they're there, just to remind you what we're doing on these days. So, any questions?
Can we complete the final lab exam and the other homeworks in advance?
I believe they are open. I need to check. There are due dates, but I think the open date, you know what? Give me a sec. I can't get in here. Let me find out. Give me a good question. Let me call up my site.
I feel like last time I checked, the final lab exam was closed. I'm not sure.
Was it closed? Okay.
Yes, I think so.
I will check it here and I will find out immediately here as soon as I get to the class. When I got Zoom opened up and my my web browser opened up, things shut down a little bit, slowed down because I got a lot of, and my laptop I guess can't really handle it. So I'm getting there. It's making its way. All right. So the homework's open. Okay, the question was for, okay, the online final lab is available, not available to the 3rd of December. I can open that up. Okay.
Thank you.
Yeah, in fact, as we speak, I'm going to open it up.
Sounds good. Thank you.
Yeah, give me a second and we will make that available. It is still due on the 3rd, but it's available. Here. Okay, it should be available now. I just opened it up. So you have now until December the 3rd to complete that, because it will close down on the 3rd.
Thank you, Dr. Fred.
Yeah, no problem. Let me log out of here. Okay, any other questions? That was a good question. I'll make note of that. You could open it up for future times. Okay, yeah, there is a course evaluation that doesn't open up until, I believe there is a day that I can't open it up. I can't change that, but do please go in there and the instructions are given. There's 2 links that you have to check. one concerned with the lecture, one concerned with the lab. And I believe all of us in the Maricopa Community Colleges, we're gonna do, I know I am, we're gonna do online one more semester for both SCC and GCC. Some instructors have opted up for back to face-to-face, and some have done like a hybrid. But for future reference, I really would like to get some feedback from you with respect to this online chemistry class. I was kind of skeptical when we first started, because chemistry, I was like, how are we going to do this online? And I'm not still 100% comfortable with it, because it's a course that you really got to do a lot of show and tell and really see it. And I used to do a lot of things on campus so you can actually see what's happening. I can't do it here at home because the ones examples I do can maybe cause my apartment complex to go up in flames, and I can't do that. So there's some things that are good, some things that are not good. So would like some very good positive feedback with respect to, what, if you were doing this class, what would you like to have changed? What would be better, given the equipment and how we have to do it, okay? Obviously, there's something, there's a lot of things I would like to do, but we really don't have the technology to do it at this time. It might be in a couple of years, but a lot of constructive criticism is appreciated. I don't have a problem with criticism, because that helps me make things better, get things better. Destructive, that's a different story, okay? So that opens up, so yeah, so you have one link for the lecture part and one link for the lab part, okay? All right. We're gonna talk about coffee. All right, coffee, basically a solution, okay? And let me get this. How do we define a solution? Well, a solution by definition is simply what we call a solute dissolved in a solvent, okay? Now, this ability to dissolve goes back to polarity. It's all related, okay? So as a general guideline, if you ever want to determine if this material will dissolve in, say, water, water is the most polar solvent that we have. And so chemicals that exhibit a polar character will dissolve in a polar solvent like water, okay? The converse is true. Molecules that have non-polar character would dissolve much more readily in non-polar solvent. And I use oil as an example. So we have oil and water. We realize it doesn't mix. Don't believe me? Look at Italian dressing, right? You look at a bottle of Italian dressing, we got two layers. We have an aqueous layer and an oil layer. And some materials in that Italian dressing have more non-polar character, so dissolve in the oil. And some of those chemicals in the Italian dressing have polar character, so they're more readily dissolved in the aqueous solution. And so when you take that Italian dressing and you mix it up, you're not really dissolving the oil and water. They will never mix. You form an emulsion, kind of a mixture, and then that's what you pour in your salad. A little bit of everything goes on your salad. But even as it sits in the salad, the oil and the water will separate, okay? Makeup. You ladies correct me if I'm wrong, but there are some makeups that are hurricane proof, right? That you will last, they will survive a hurricane with respect to being washed on. And then there's some makeups that you require some some heavyweight oil to get off because of the polarity. So it's a function of polarity. But we'll get to that here in a bit. Okay, so the solute is normally whatever chemical is in the smaller amount, okay? And the solvent is whatever chemical is in the larger amount. Now, we tend to think that solvent is normally a liquid. And that's okay. You know, just like when in the beginning, you probably always thought that salt was just sodium chloride. Now, hopefully you realize that the term salt with respect to chemistry is really represents any ionic compound. So the solvent, yes, it could be a liquid, but it can also be a solid. And we'll get some examples here in a bit. The water is the most common solvent. Now, this is pretty self-explanatory. You know, here's a color solution of a liquid, and you can see the intensity of the color, which is proportional to the concentration. It makes sense that that color to the far right is more concentrated than the color to the far left, that light pink color. So whatever solute is in there, the concentration for the light pink color is much less than obviously the one on the far right. Okay, and we use this kind of technique a lot when we're measuring the concentration of colored materials, because this curve, we can create a curve and measure the absorbance of light in these different concentrations and generate a graph, and we can determine the concentration of many unknowns, you know, based on the intensity of the color. Okay. All right. So some examples of solutions. You can get a gas in a liquid. Classic example is a carbonated soda. Okay. You have carbon dioxide, which is bubbled into the solution. And we know that carbon dioxide is not really soluble in water. Why? If you recall, carbon dioxide by nature is nonpolar. Remember that we determined that the poles, the polar bonds of carbon and oxygen go in opposite direction and they cancel each other out. So the net effect is that carbon dioxide was nonpolar. But nevertheless, it will dissolve to a certain extent in water. And the same is true for oxygen, which is a good thing for fish, right? All right, but you also know it's not strongly dissolved in water. Why? If you take your soda pop and you shake it, what happens? You build that carbon dioxide essentially gets kicked out of the water solution. You build up pressure and you open up the cap and you got a big mess. So a gas in a liquid is an example of solutions. Okay, and you have a liquid in a liquid. So you got a mixed stream. Alcohol is polar, and you put it in an aqueous solution, tonic solution, for example, or water. It will dissolve because the polarities of the two are very, very similar. You can have a solid dissolved in a liquid. Table salt, sodium chloride, ionic, soluble in water by definition of the solubility rule. Sodium chloride is soluble, so we create a saltwater solution because the solubility is sodium chloride. We can have gas in a gas. For example, the air around us is really a mixture of multiple gases, with nitrogen and oxygen being the higher percentage. And then there's all kinds of different trace gases, carbon dioxide, all kinds of things, methane. So, but it's another example of a solution. You can have a solid in a solid, okay? A lot of the alloys of metals are not, like, for example, the steel utilized to build buildings is not pure steel, because pure steel by itself is worthless with respect to building any structure, because pure steel is very soft. Just like the gold that you may have in your jewelry that you have. If it's a gold ring, it's not pure gold. Pure 100% gold is very soft, and you can smash it, and then it wouldn't make a good ring. The moment you smash your finger, that ring will collapse. And so what happens is we put other metals inside the metal. So, for example, steel is a combination of iron with a little bit of carbon in different concentrations or different alloys. Brass is a combination of copper and zinc. Okay, and so that's another example of a solution, even though they're solid in a solid. So those are some classic examples of different types of solutions. Now, earlier I mentioned to you about polarity. Now, the rule is like dissolves like. So nonpolar material will dissolve in nonpolar solvents, and the converse is true. Polar solutes dissolve in polar solvents, okay? So if that suggests, this suggests this. Recall the solubility rules? We had the rules that told us that this particular compound is soluble, okay? And these other ones are insoluble, even though everybody is an ionic compound. So technically, being ionic compounds they all should go and dissolve in solution, but they don't. The solubility rules tell us that they do not. Like silver chloride is insoluble. But that would suggest that silver chloride has lost some polarity, if you will, becomes less like water, and therefore it becomes more insoluble, even though it is an ionic compound. Okay. Nonpolar solutes dissolve in nonpolar solids. Okay. Classic example is we have oil spills, where you can see the mess because the oil, which is nonpolar, will not mix with the water, which is polar, which really causes the problem. So when we have two liquids that mix well, because they're both of the same polarity, because they're liquids, we use the term miscible rather than soluble, insoluble. Okay, so there's a subtle difference that is used in science. So when two liquids have this mix well because of their respective polarity, we call it miscible. They're miscible with each other. If they do not mix, because again, due to the polarity, that we classify that as, or describe it as immiscible, okay? And when we deal with solids and liquids, when the solid dissolves in the solvent, in the liquid, then we use soluble term, or insoluble, okay? So note the difference. Dealing with liquids and liquids, it's either miscible or immiscible. Solids with liquids, it's either soluble or insoluble, okay? So we may have a table sitting here, and we're asked to, will the solutes dissolve in these respective solvents? Well, to answer these type of questions, the thing that you have to do is determine the polarity of the material, okay? Determine the polarity of the solutes, and then determine polarity of the solvents. And so if we look at ammonia, NH3, recall that we did the Lewis dot structure for this, and we ended up with, let me change the color here for a second. The Lewis dot structure, sometimes you need that to determine the polarity, and we ended up with this particular structure. And the most notable thing we also, if you don't remember, if you hopefully remember, that we ended up with a lone pair of electrons in the central atom. And at that point, I said, you know what, when that happens, without question, you don't have to go any further. You have a polar solvent, in this case, polar molecule, okay? So the polarity of ammonia is polar, okay? Now, we go to the next one, C12H26. Well, we may not know what C12H26, it could be an infinite number of compounds. They are. There's numerous combinations that you can, of chemical compounds that you can do that end up with a formula, general formula of 6 carbons, and there's 26 hydrogens around it. But the thing to remember with respect to polarity of both the bond and the molecule was that we said that carbon-hydrogen bonds are nonpolar, okay? Because their respective electronegativity of the carbon and the hydrogen are essentially the same. Therefore, they're zero, much like the diatomic molecules. That's what we got down here, diatomic. This guy's diatomic bromine, and that means that both atoms are the same, so there's an equal pull of those electrons in that bond. And so these diatomics are nonpolar. All diatomics are nonpolar in nature. Well, going back to C12H26, carbon hydrogen has been classified as a nonpolar bond, and there's nothing else in here other than carbon and hydrogen. So it is a hydrocarbon, resulting in this species is nonpolar. Okay, so now we have defined the polarity of the solvent. Ammonia is polar, C12H26 is nonpolar, and bromine, being diatomic, is nonpolar. Okay. Now we look at the solutes. We have HCl, hydrochloric acid. Okay. We have hydrogen and chloride bonded. Automatically, two different atoms, we have a polar bond, which results in a polar molecule in this particular case. There's only two atoms. Okay. So HCl is polar. Okay. I2, well, I2 is iodine, diatomic again. Okay. Now, bear with me. Iodine is diatomic, like Br2 bromine. So therefore, this I2 is nonpolar. Okay. Now, PCHCl3, we may not know what that is. So what you got to do is you go back to the Lewis dot structure and generate the Lewis dot structure for phosphorus trichloride. And you'll see, you don't have to go that far, but you can, by analogy, realize that, okay, we did ammonia with nitrogen, and guess what? Phosphorus is right in the same group, right below it. We're going to end up with a formula which is just like we just did for ammonia. And we're going to have phosphorus with a lone pair, and we're going to have the three chlorides bonded to them, and then those lone pairs on the chlorides. We're going to end up with a structure like this. Key point being that we have lone pair on the central atom, which automatically tells me I have a polar compound here, polar. I got three polar bonds, and then I got the lone pair. It is polar. Okay, so PCl3 is polar, iodine is nonpolar, and HCl is polar. And finally, we do the last one, just like we did the analysis of C12H26. We may not know what CH4 is. I'll tell you it's methane, but if you didn't know what it is, recognize that you have nothing but carbon and hydrogen in that molecule, which means nonpolar bonds all over, which means we have a nonpolar solute. Okay. So once you have defined the polarity of all the chemicals that are involved, now you can determine whether they're going to be soluble or not, whether that solute will dissolve in that solvent. And that will be simply based on the polarity, and remembering that light dissolves light. Polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. Okay. So that's what we did there, which is what? Which then defines, I mean, now you can see it out of my writing into writing that's more readable. Okay, so we had defined the polarity of all the parties involved, and now we look at it. We got polar and polar with respect to the first one, so yes, HCl will dissolve in ammonia, okay? And iodine will not, because iodine is nonpolar, and ammonia, NH3, is polar. Yes for the next one, because they're both polar, and no for the last one, NH4, CH4, methane, because that is nonpolar, and ammonia is polar. Okay. With respect to the nonpolar solvent, it's obviously anything that's polar is not going to dissolve. So the iodine and the CH4 will dissolve in C12H26 because of the polarity of each one, whereas the other two, the answer is no. And the same is true for bromine as the solvent, all the nonpolar solutes will dissolve and the polar solutes will not, okay? And so if you're ever given a table or you're just comparing any chemicals and ask the question, will chemical A dissolve in chemical B? Well, to answer that, you need to figure out the polarity of A and B, and then remember, like dissolves like, okay? All right, so we also use the term miscible, immiscible. And so if we have a polar liquid and a polar solvent, they're both going to be miscible, okay? Because we're dealing with salt, liquid and liquid, okay? Immiscible for the nonpolar solid. Nonpolar liquid, immiscible for a polar solvent. Here we're using the term solvent as if it were a liquid. I should clarify that. We're talking about liquids here. But even if we weren't talking about liquids, even as long as we know it's polar versus what it amounts to is being either polar versus nonpolar. Okay, immiscible for nonpolar liquid, whereas miscible for a nonpolar solvent. Again, due to the polarity of the material. Polar solid in the solvent, soluble. Polar solid in a nonpolar solvent, insoluble. A good example of this would be a polar solid like sodium chloride, table salt, and polar solvent like water, okay? If you take the polar solid like sodium chloride and dump it in some oil, what do you think is going to happen? Nothing. It won't dissolve. Sodium chloride won't dissolve in oil, okay? Nonpolar solid, insoluble in a polar liquid solvent. Nonpolar solid, soluble in a nonpolar liquid solvent. If it's an ionic solid, well, it depends on the solubility rules, whether it's soluble or insoluble, okay? And it's obviously insoluble if the ionic compound would be insoluble if it's an ionic compound with a nonpolar solvent. This picture here just basically just kind of show you what's going on when things are being dissolved by a liquid. And the classic example that most everybody uses is water and the ionic compounds like sodium. You can see that the partial negative side of the water molecules are solvating the positive charge of the sodium ion. At the same time, on the other side, you have the chloride, if this were sodium chloride, and those are being stabilized by the positive part of the water molecule, okay? All right. Which brings us to concentration, okay? Concentration is simply a ratio of solute over solvent times 100, okay? And we call that mass percent. Now, there's also what we call molarity, and we introduced this way back when we were doing pH. Remember that, pH? Okay, and remember we had the hydrogen cation with the brackets around it. That was concentration, but that, we told you we're going to talk about it more later on. Well, here we are, okay? Concentration in this particular case is given as molarity, and that is a ratio of moles over volume in liters, okay? So you could be given grams of some compound, and you need to convert that to moles, okay, of some compound, X. And then given the volume, you got to make sure that that is in liters. And now you got the moles over liters, and that gives you molarity, okay? Mass percent, simply just a weight ratio. And sometimes a lot of the mass percent you may be familiar with. There are a lot of wines out there, for example, I use that as an example, or even alcohol drinks like beer. Those are percentage, of alcohol over the volume. Sometimes those are mass over volume. Sometimes they're volume over volume. Some are mass over volume combination, but we're going to deal simply with weight over mass with respect to mass percent. Okay, so how that is defined. Well, we take the mass of the solute and we divide it by the mass of the solution. Okay, that's important. This is important. The mass of the solution incorporates the mass of the solute and the mass of the solvent. Okay, not just the solvent, but the combined mass of the solute and the solvent. So for example, we're going to calculate the mass percent if you took 15 grams of potassium nitrate and we dissolved it in 135 grams of water. Okay. Remember here, we're asking for mass percent. So we don't really need to know what the structure is for potassium nitrate. Okay. We don't need to know anything about moles. All we need to know is how many grams of potassium nitrate are used and how many grams of water are used. That's it. Then we plug it into the calculator where we got 15 divided by the sum of the potassium nitrate and the sum of the water times 100 gives us a 10% solution. Okay, 10% solution. Those of you in the nursing field, you may be dealing with a 0.9%, what is called saline solution. Okay, big old bag of water, look at the water being injected into your patient. It is a 0.9% of sodium chloride solution and is calculated very similar in this manner. It is 0.9% for a particular reason. Anything less can cause destruction of the cells. Anything more can cause destruction of the cells. So 0.9% is just the right percentage that none of the cells are being destroyed by the saline solution. Okay. So in this example, it's a 10% solution for potassium nitrate. Okay. Sometimes you may be asked the question of how many grams of water are needed to make a 5% solution, okay? And so they're asking you for the grams of water. And they're telling you the percentage and they're telling you how much salt. It's some salt that is utilized. So we're trying to figure out how many grams of water we have. So we had to set up a kind of a simple algebraic equation, okay? Where we know that going back, let's go back to this one. Where are you going? Right here. Notice in this example we just did, we know there's 15 grams of potassium nitrate here and here, but we don't know what the amount of water is. So we can actually set up an algebraic equation to figure out what the grams of water is, okay? Knowing what the formula is to calculate the percent. And so we're going to set that up as follows, okay? We know we are given 10 grams of a salt, and we don't really care what salt it is. We know it's a salt. That's it. So it's 10 grams, and that is divided by 10 grams plus X. X is what we don't know how much water, how many grams of water. So that is what we're doing. We know it's 5% because we're given 5. And we know the entity to the right of the equation, if we multiply that by 100, gives us the percentage. So we're in essence set up a very simple algebraic equation. Now, we need to solve for X, okay? Now, solving for X, in algebra, there's a lot of ways to solve for the variables. This is just one way, okay? All right, so you can take that equation and you get to this point. You might ask, whoa, wait a minute, how did they get from number 1 We're going to call this equation number 1. Now we get equation number 2. How did it get from equation number 1 to equation number 2? Okay, well, if you look at this carefully, what they did is, you see this entity right here? They took and multiplied 10.0 plus x on both sides. 10.0 plus x times 5. It cancels here, leaving us with 10 times 100, which is right here, leaving us with 10 plus x times 5.00, which is right here. See how they did that? Okay. So they got rid of the denominator of 10 plus x, multiplying it by 10 plus x on both sides to simplify the equation. All right, then they go to the next equation. All right, so this we call this equation number 3. Well, what they do here, no big deal. What they did was multiply 100 times 10. It gives you 1,000, right? Okay, now at this point, you could do multiple things. You can distribute the 5 times the quantity of 10 plus x. That's one way to do that. Or you can go this way and get to this point. But what did they do here? They divided through by 5.00 on both sides. And that canceled that out over there. That results in 10 plus, this is equation number 4, 10 plus x equals 1,000 divided by 5. Okay. When you do that, you get 200. 10 plus x equals 200. Okay, so that's step number 5. Now here, now we're just going to solve for x. A couple of ways to do that, right? Well, actually one way. Well, the thing is you get a negative x here, right? So we can take the negative x and move it over to the right, okay, to give us a positive x, and then move the 200 around. Your result is this. You end up with x equals 190, which is the answer. And we put it in scientific notation simply because our answer should be in, we're working with 3 sig figs, right? And 190 is not 3 sig figs, so we put it in scientific notation, 1.90 times 10 to the second. And that is the answer. You need 190 grams of water, 10 grams of salt to give you a 5% solution. Now, how do we know if that number is correct? Well, you take your answer, okay, and you plug it back into the equation. Let me clear this up a little bit, clear my mess. So if you take your answer of 190 and plug it in right here, 190, and do the math. If you do the math, you should end up on both sides to be 5.00 is equal to 5.00, which is a true statement. 5 does equal 5, okay? If you, on the right side, you come up with a different number, then 1 or 2 things, you didn't do the math over here correctly, or your 190 that you calculated is incorrect, okay? But in this case, 190 is the correct answer to make a 5% solution. All right, so clear this. All right, any questions about that one? That is the mass percent. Okay. All right, molarity. Molarity is nothing more than another ratio again. Here we go again with these ratios, right? But the ratios here are moles over liters. So if you're working with moles, guess what? Maybe you need the molar mass, right? Remember we worked with molar mass? So now in the previous case, when we were doing potassium nitrate, we didn't care about the structure. Here we do. Why? Because we need to determine the correct molar mass. Because with the correct molar mass, we can now calculate the number of moles for X number of grams. For example, it says calculate the molarity if you took 9.99 grams of potassium bromide and you dissolved it in water to make 2.5 liters, okay? And see, so keep in mind, it says calculate the molarity. So it's capital M is equal to moles over liters, okay? You're given the liters right here. So automatically you can do that. But you need to calculate the number of moles of potassium bromide if you're given 9.99 grams. Well, we need to make sure we write the correct formula. As always, we write them in ions first. Potassium ion is K plus, right? We know that because potassium is in group 1, has a +1 charge. The bromide, we know that bromine is in group 7. When it becomes bromide, it picks up 1 electron. So therefore, its formula, its ion is a negative charge, -1 charge. So now we got them in ion form. We can put them together as a simple 1-to-1, okay? And now to figure out the molar mass, you look up the atomic weight for potassium, atomic weight for bromide, and you have the molar mass. Okay, so that adds up to 119 grams per mole for potassium bromide. We're going to divide, we got grams. Remember, if I got grams, I want to get 2 moles, I divide by the molar mass. So I'm dividing by 119.00 grams, and that gives me 0.08395 moles. Now, don't truncate anything. Don't do any rounding until you're done with the mathematics, okay? And here you have, you're going to divide that by 2.50. Okay, so you're going to have at least, you got 3 sig figs to begin with, and here with 9.99 grams and 3 sig figs in the 2.59, you're going to end up with 3 sig figs in your answer, okay? And that answer is, the molarity is 0.0336 moles per liter, okay? Moles per liter. And that is the that is the molarity of a solution of potassium bromide. Specifically, if you take 9.9 grams of potassium bromide, you weigh that amount down, and then you dissolved it in exactly 2.5 liters of solution. The molarity of that solution would be 0.0336 moles per liter, okay? Moles per liter. That is, in every liter of solution, you're going to have 0.0336 moles of potassium bromide. All right, I think we got one more. All right, so this one says, calculate M, capital M, molarity if you take 5 grams of sodium phosphate and you dissolve it in a solution of water that is 255 moles per liter. So keep it in mind, moles is defined as moles per liter. We're dealing with 255 milliliters, okay? Remember that in 1 liter, there is 1,000 milliliters. So we're going to need that converting factor. Second of all, we're going to need the molar mass of potassium phosphate, sodium phosphate. We know that sodium is Na, like the previous example. It's a group 1, like potassium, it's a group 1 element. Okay, it will have a +1 charge. Phosphate is a polyatomic ion. If you recall, go to your polyatomic ion table. It has a -3 charge, which tells us that we're going to need 3 sodium ions for every 1 phosphate ion. So our formula becomes Na3PO4. And we need that because we need to know we got 3 sodiums, we got 1 phosphate, we got 4 oxygens. And that will give us the molar mass. So it's important that we figure out the formula, right? Because without the correct formula, we don't know the molar mass. We don't know the correct molar mass. We don't know the correct number of moles that we need to work with. All right. Let me clear the mess up a little bit. Okay, so we take, after we figure out the formula and we figure out the molar mass, that molar mass is 163.94 grams. Take 5 divided by the molar mass gives us 0.0304986 moles. And I'm pretty sure there's more numbers out there, but like I stated, don't truncate anything until you're done with all the math, okay? Keeping in mind that the numbers that you had initially is 2 sig figs up here for 2.5 and 3 sig figs right here. So that means that at the end, your answer should have no more than 2 sig figs, okay? Keeping that in mind based on what you started off with. So you write down all the numbers that you're given, and then at the end, then you're going to truncate like we've been doing to the correct number significant figures. We need the volume, so we take the 255 milliliters and we divide that by 1,000, okay? Remember, this whole system, we're setting it up so we keep track of our units. Notice we got milliliters to cancel. Notice at the first one, we had grams that cancel out, leaving us with moles and liters, which is what we need because molarity is moles over liters. Yes, it's been shown that you can have millimoles over milliliters, but the units have to be similar. Okay, so, but don't worry about that. Just keep in the units of moles over liters, and you'll never be incorrect. You won't be confused. Okay, because what happens at times is this. People forget to convert the milliliters into liters. So what they do is divide this by this. And yes, the number is going to be close, but they're going to be off by their decimal place will be off. Okay. And so the answer we have here is 0.12 moles per liter. That is the molarity of 5 grams of sodium phosphate dissolved in 255 milliliters. Okay, 255 milliliters of solution. All right, well, tell you what, guys, congratulations. Another one bites the dust, so to speak. And chapter 15 is done. I told you it was very short. What do we got here? Don't forget the assignments, okay? There's a practice final exam on the website, okay? And I'm not good looking yet because you got one more chapter. For some reason, I don't know, SCC requires that you have one more chapter dealing with gases, and GCC, they stop at 15, so. All right, we got one more, and that's a very short chapter. And we'll complete that next time we meet. All right, so at this point, I'm going to stop it here as far as